So we're starting the last 2/3 of this unit and the last main topic in this course, waves. All right, now, waves have a lot of similarities to simple harmonic motion because they are caused by an object undergoing simple harmonic motion. Okay, it's an oscillation. Okay, that's what a wave is. All right, so we're going to look at the characteristics of the two types of waves. Okay, the two types of waves are transverse and longitudinal. I did spell that right. Every year somebody tells me, Coderre, it's longitude. No, those are lines on a map. Longitude is different. Okay, so just so you know, longitude and longitude are different. Okay, so we'll be looking at that. We're going to look at how waves are created and, more importantly, how they're propagated. That is how they continue to travel. And we're going to look at the various properties of waves, which, as we already said, are very similar to the properties of a simple harmonic oscillator. We'll be talking about things like period, frequency, amplitude, equilibrium position, okay, all of that kind of stuff still applies to waves. Okay. In space, no one can hear you scream. Why not? There's no air. How does there being no air prevent you from hearing anything? What's that? Okay, sound bounces off stuff, that's true. Okay, but sound is a what? It's a wave. And waves need a medium in which to travel. The exception being light waves. Okay, because light is both a wave and a particle, it's its own medium and can travel through the vacuum of space. No other waves are able to do that. Right? Sound waves can't travel through space because there's no material for them to disturb. Okay, because what a wave really is a traveling disturbance. Something disturbs a medium and causes that medium to oscillate. Right? So when you throw a rock in the pond, you get those waves because the rock disturbs the pond, the water downwards. Okay? Water is somewhat elastic, so it rebounds after the disturbance and oscillates until the energy is gone. Okay? So we see those waves, multiple waves travel outwards because the medium, the water, has been disturbed. Okay? And that the energy of that disturbance travels outwards in all directions. Everybody all right with that idea? Okay? So a wave requires a medium in which to propagate. As long as there's a material there, a wave should be able to travel through it. Okay? Can waves travel through all things equally? No. And it actually depends on what kind of wave it is. Right? Longitudinal waves, like sound, tend to travel through dense objects more easily. Transverse waves, like light, tend to travel through dense objects less well. Right? So they actually work opposite each other because of the nature of the waves and the nature of the way they disturb the material. Okay. All right, so like we said, a wave is very simply a traveling disturbance. Does a wave carry energy? Can a wave do work? Yeah, it can lift up a big ship if it passes underneath it. Okay, a wave has energy. It is a traveling disturbance. To disturb something, you have to do work on it. Okay, so all a wave is doing is taking the energy of the disturbance and moving it away. All right, so yes, a wave is or does possess energy. Okay, in fact, really a wave is energy, okay, as opposed to a wave being matter. Right, a wave isn't actually matter. A wave travels through matter. Okay, everyone kind of follow me there on the difference? Because a lot of people, they visualize a wave, they picture a tidal wave, right? And they're like, there's the wave. Well, actually, no. There's the medium the wave has disturbed. Run now. Okay, because it's a big wave and they're dangerous, right? So we have to remember that a wave is not its own thing. It's actually just the energy of a disturbance moving through something else, which is why if a speedboat goes past someone who's just floating in the water, okay, that person floating in the water will oscillate up and down. It takes work to move them up and down, okay, and that's the energy from this disturbance traveling outwards from it. Everybody all right with that idea? Okay. Now, the other thing we need to remember is that a wave is not a bulk movement of water like a river. Okay? In a river, water moves from point A to point B. In a wave, the water does not move from point A to point B. The wave moves from point A to point B. What does the water do? The water moves up and down. Okay? So as a wave travels through the water, It lifts up, goes back down, and then returns to equilibrium. It simply oscillates up and down. That's it. The wave does not actually travel horizontally. All right. That's why if you're like floating in the ocean and a wave passes over you, okay, you just go up and you come back down and you're still in the same spot. Now, can a wave push you inwards? Yes, it can. If you're on the right part of it, you're paddling a little bit and you can slide down the front of it due to gravity. Okay, but that's not actually the wave pushing you inwards. That's you using gravity to go down the wave because of the potential energy the wave has given you. Right now, we have a real problem with this because we visualize waves as moving in, right? If you're standing on the beach, you see the water come in and you see the water go out, right? But we're not really seeing water moving from A to B. We're seeing that water has moved upwards and then the wave that disturbed it ran out of water, okay? Because it got to the shore. So the wave actually moves out of the water and into the air. We don't usually feel it because it's quite small. If it's a tidal wave, like a really big one, you would feel a shock wave when the wave actually leaves the water and enters the air. Okay, if you've ever seen any like big disaster movies, okay, when there's like a meteor impact or big tidal waves, okay, people are at the ocean waiting to die and they get blown away before the wave crashes. That's because the wave leaves the water, okay, travels into the air instead. So now there's been all this energy that's lifted up the water column that's now gone. What's keeping the water column up? Nothing. So it crashes down. What you see is the splash. Okay, so as the water descends back down from that point of high potential energy, it splashes down, and the splash is what moves inwards. That's what a tidal wave is. Okay? When a tidal wave inundates an area, it isn't a big white curling monster. Okay? It's just you see the ocean come in and swallow things up. Okay? Because it's moved upwards and then lost the energy that held it there. It comes down and then the water rushes in, okay, and inundates the land nearby. Everyone follow me there? Okay, I'll show you some videos of that here in a little bit. All right, so wave gets transmitted, or energy gets transmitted through the wave can do work. Okay. All right, so there's two kinds of waves, transverse waves and longitudinal waves. So a transverse wave is called transverse because the wave and the medium move 90 degrees or transverse to each other. Okay, so when I make a transverse wave, I disturb the medium up and down, and the wave travels through it this way. Okay, so the medium is just doing this, but the wave is doing this. It's much easier to visualize this in a spring because you can tell that a spring, when you're making waves in it, isn't actually moving from there to there. If it did, it would jump out of your hand. Right? So it's just, the spring is just moving up and down. The result of you moving it up and down moves along the spring in the other direction. Okay, so all we see here is the wave moving this way and the medium oscillating up and down. In fact, if you put a piece of tape or a marker on a slinky and you do that, you just see the marker go back and forth. The marker doesn't move away from you. It doesn't move towards you. Okay, it just moves up and down. Everybody all right with that idea? All right, now, waves carry energy. And we see obviously evidence of that in tidal waves and things like that. Where else do we see that waves carry energy? Okay, microwaves. Yeah, we can use the microwaves as they hit the food with high rate of speed transfer that becomes essentially thermal energy. Okay. Okay, solar panels are taking they're taking more the high speed of the light of the photons as opposed to waves, but similar. What about sound? Can sound do work? It certainly can. Okay, your generation is going to find out more about that than any generation before you. You know why? You guys are the iPod generation. You guys use earbuds and headphones more than any generation before you. You guys will probably have the highest incidence of hearing loss of any generation simply because of that. Okay, like my generation, we had the Walkman, right? But you couldn't wear the Walkman all the time because the Walkman had like 6 AA batteries in it, and it turned a tape player, which only lasted about an hour and a half on the 6 batteries, okay, before it was dead. So you could only listen to it a little bit each day before you were replacing the batteries. But you guys, I mean, you can listen to yours all day long. Okay, the technology is better, and you've got your earbuds right in your ear, or you got big beats that are right over top, and they're cushioning and sealing in your ear. Okay, when we had Walkmans, they had those like orange foam, like thin wire things, okay, that didn't channel the sound very well into your ears, so they weren't efficient. They didn't damage our hearing to the extent that modern ones can. Okay, in fact, so much so that one of Apple's updates was to limit the output of their stock earbud earphones, so that they could not be damaging to people's hearing, because they were afraid that in the future they'd get lawsuits over that. Okay, so it's something to consider, okay, when you're listening to your headphones. In fact, I'll demo. So waves can carry energy, okay? They can do work, right? You can see that, sometimes even sound can shatter glass. Okay, if it's really, there's a really loud sound can even shatter glass. Okay, that's pretty rare, but you'd have to be pretty intense. All right, so what we start out with here, guys, is just properties of waves, and then I'm going to show you these other videos here. Okay, so we got a wave follows this pattern, which looks very much like the pattern that we got for a simple harmonic oscillator. Okay, so we use the same terminology. The maximum distance from the undisturbed position of the medium is the amplitude. Okay, amplitude represents energy in a wave. The bigger the wave is, the more energy it carries. Speed actually has very little to do with the energy of a wave, because all sound, regardless of how loud it is, travels at the same speed. Okay? Speed of a wave is controlled by the medium in which it travels. So it doesn't matter whether I'm yelling at you or whispering to you, the sound takes the same amount of time to get to you because it travels at a fixed rate through air. Okay? There's no like kind of kinetic energy of a wave. There's the potential energy of a wave in its amplitude. Okay, so amplitude is where we measure, okay, the intensity and energy of a wave. So when you turn up the volume on something, you're increasing the amplitude of the waves. You're not making them travel faster. Okay, because if that was true, you could whisper something awful to somebody and then scream something really nice, and they wouldn't hear the awful thing you said because the scream would get there first. Obviously, that doesn't happen. Okay, so all waves are going to travel at the same rate. Okay, then we've got new terms. The high point of a wave is called the crest, and the low point of the wave is called the trough. Okay, they're equidistant from equilibrium. Okay, one's just the high point, one's the low point, but they're equidistant. Okay, amplitude is the same high or low. The length of one wave is called the wavelength, oddly enough, the length of a wave. So, okay, one wave is one complete cycle. So it's got to go through equilibrium, down to the lowest point, back through equilibrium, up to the highest point. So that would be one wavelength. Okay, I'm just going to draw a line here that's one wavelength long. The distance between any two equal parts of the wave is a wavelength. So you can see here as I move this, okay, one wavelength is the distance between two crests, two troughs, okay, two equilibrium positions, okay, that's one wavelength. Everybody follow me there? All right. Okay, so we'll watch a couple of these videos. One's on tsunamis, one's on big waves. Okay, the big waves one is like this scientist who's like a surfer. So he's saying all the scientific stuff in like the surfer dude voice. It's really a juxtaposition of things. A minute. So the thing that happens here, guys, and the reason again why we have kind of a misconception about how waves work is that we know that out in the deep ocean. So if this is kind of the ocean floor here, okay, so this is like the shore, and then it gets shallower, and then you got kind of the continental shelf out here, so the really deep ocean. Okay, if you've got a tidal wave or a really big wave coming in out here in the deep ocean, that wave might only be about that tall, right? When that earthquake happens, I mean, the most that the crust is going to move is a few meters. Okay, so you'd be looking at something that might only be 3 to 5 meters tall out in the open ocean, and that would be a big one, right? But we see that as that wave gets closer to the shore, what happens to it? It gets bigger. Okay, well, actually the wave doesn't get bigger. What happens to it is it starts to have less water, and when there's less water, it slows the wave down. So what happens is the front of the wave slows down, the back of the wave catches up, And you still have all this energy, but less water to have it stored in. So the wave just rears up as it gets close to shore. So yes, it gets taller, but it doesn't have any more energy than it had before. It just looks that way because now it's slowing down. So the wave is compressing, okay? And the only place it has to go is up. It can't go down because that's the ocean floor is down there. So it pushes it up and it gets taller as it approaches the shore. Okay, does that sort of make sense? Because we always see that, right? The waves they're out there in the deep ocean, there's nothing happening, but there's all these big waves crashing on the shore. It's just because of the change in depth. It changes the speed, so it changes the height, and we see them more obviously. Okay, so now I'll show you the big waves, dude. All right, so we've seen a few of those kind of examples. Those are all transverse waves. Everything we watch there is a transverse wave because it's disturbed upwards but traveling forwards. Okay, longitudinal waves are called longitudinal because they're parallel. So the disturbance is back and forth, and the movement is forward. All right, so they're in the same plane rather than 90 degrees to each other like the transverse waves were. Okay, so a longitudinal wave is a compression and a rarefaction. So sound waves are longitudinal waves because if you ever watch a speaker, okay, like a sub move back and forth, it's compressing the air and then rarefying the air, compression, rarefaction, okay, back and forth, back and forth. So these waves travel in the same direction as the disturbance is happening. Okay, the air still doesn't go from A to B. Okay, the air just oscillates back and forth, right? But the wave travels from the speaker outwards. All right, so those are longitudinal waves, and they're made of compressions and rarefactions. Okay, so a compression is the dense area, and then a rarefaction is the less dense area behind it. All right, and that's what you see when a speaker moves back and forth. Okay, it creates a compression, then a rarefaction, compression, rarefaction. Okay. All right, now again, remember that the medium itself doesn't move. So if we take this slinky and we make a longitudinal wave in it by pushing it back and forth, okay, and we mark one of the links in the slinky, that link will move ahead of equilibrium and then behind equilibrium and then return as the wave passes through. So a longitudinal wave, even though it doesn't go up and down, still has the same, like an amplitude. Okay, it has a period, it has a wavelength. Okay, the wavelength would be the distance, okay, essentially between here and there. Okay, that's the compression and the rarefaction rather than the crest and the trough, but it's still the same kind of properties. Okay. All right, everyone okay with that idea? Okay, so both transverse and longitudinal waves are periodic waves. That is, they have a period, a frequency, okay, all of that kind of stuff, okay, because they come from a source that is experiencing simple harmonic motion, right? So the source is vibrating back and forth or oscillating back and forth, causing the waves to happen. Okay. So we'd see something like this, okay? We have, again, that wavelength that we were talking about before, so that's the length of one cycle, all right? What do we call the time it takes for this cycle to go by? Period. How many cycles go by every second would be? Frequency. All right, so those are things we have to remember. And then obviously amplitude, okay, is the maximum distance that the medium moves from its undisturbed level. Okay, so we've talked about that. We know what amplitude is, okay? So amplitude, remember, is the distance between a crest or trough, okay, and the undisturbed position, okay? And it represents, so we should probably write this in, okay? Represents the energy of a wave. Okay? The greater the amplitude, the greater the energy that wave has, because in a certain medium, speed is fixed. Okay, I can't make a wave travel faster than another wave in the same medium. Their speed is going to be fixed. Right, and we'll actually do a little thing with that probably tomorrow, okay, where we'll take some slinkies out and we'll make waves of different sizes and whatever, and you'll see that if you make a big wave, you make a small wave, they don't catch each other. Okay, they'll dissipate because of friction against the floor, but a big wave is not going to travel faster through the slinky than a small wave. Okay? Only way to make a wave travel faster is to change the medium. So if I had the slinky really loose, the waves would travel really slowly. Then if I tighten the slinky, they'll travel faster, okay? Because now there's more tension in the medium. I've changed something about the medium, and as a result, the wave will travel faster, okay? Same is true for air and air temperature. All right, so if I have cold air, for example, sound travels at 332 meters per second in air at 0 degrees, but 343 meters per second in air at 20 degrees. Right? So the warmer the air, the faster the sound will travel through it. Right? So properties of the medium are what govern how fast the wave is going to travel. Okay, so like we said, wavelength, this symbol here, guys, is lambda. All right, we've already encountered how in physics we use the same letters over and over again. We've already used L to denote length, so we don't want to use L for wavelength. So we went to the Greek alphabet. Okay, lambda is the Greek letter L. All right, so you don't have to draw the nice little fancy curls on your lambda when you draw lambda. I just draw lambda like this. It's a short stick holding up a longer stick. Okay, and that's all you have to do to make lambda. Right, you don't have to put the little curls on there. Okay, so it's the distance between any two successive equal points on a wave. That could be one crest to the next crest, one trough to the next trough, okay? Equilibrium going up to the next equilibrium going up, and so on. And the reason I say that is, okay, this point and this point do not have one wavelength between them, even though they're both equilibrium. They're not equal successive points. They're successive, but they're not equal, right? In this position here, the wave is moving towards equilibrium. Here, like from an upward position, here it's moving towards equilibrium from a downward position. So this would be the next successive equal point, and thus this is one full wavelength. Okay, everybody follow me there? Right, and then we talked about period. Period's the time for the wave to go by. Frequency is the number of waves that go by every second. Okay, just as long as we keep those ideas straight. Remember, frequency is 1 over t. We're going to use t equals 1 over f and f equals 1 over t a lot when we're dealing with waves here. Okay. All right, so a good analogy would be a train. Okay, if we're trying to kind of keep all this stuff kind of straight in our heads, okay, the speed of the train is the speed of the waves. Okay, the length of each car is the wavelength. Right, the number of cars that go by every second is the frequency. The time it takes for one car to go by is the period. Okay, so that's just an analogy if you're having trouble kind of visualizing it in your mind. Now, the big things about a wave as it travels are speed, frequency, and wavelength. Okay, those are the big things. We'll talk about the universal wave equation that governs this tomorrow. Right, but if I slow a wave down, then these other factors might have to change. Would you agree? Okay, here's the weird thing though. The frequency of a wave never changes. It doesn't matter what you do to a wave. You cannot change its frequency after it's produced. You can change its speed, you can change its wavelength, but you cannot change its frequency. All right, that would be the equivalent of if I have a blue light that's shining on something, and halfway on its way to somebody, it suddenly changed to red. Okay, can I change the color of a light once it's produced? No. Okay, that's because the color of light has to do with its frequency. I can change the speed of it, I can change the length of the waves, but I cannot change its frequency. Right? It's the same with sound. Once I produce a sound, that's the frequency that sound is going to have no matter what. I can't change it after it's produced. So what we have happen is something like what happens out here, where the speed limit changes from 100 to 60 for some reason. Okay, so we've got the 100-kilometer-an-hour area. (100 kilometers), and then we got the 60. Weird. Okay, then we got the 60-kilometer-an-hour area. If I've got 3 cars out here, that's not cool. Okay, and they're, they got like a kind of a proper following distance out here at 100 kilometers per hour. Obviously, one car gets to the change in speed limit before the others, so it slows down. So a little while later, what am I going to see here in the 60-kilometer-an-hour area after all 3 of these have passed into it? They're going to be closer together, right? You maintain your following distance as a unit of time, right? You're supposed to have your 3-second following distance, okay, between cars. But at 60 kilometers per hour, that following time is a smaller distance. Everyone okay with that? Here's the weird thing. If I'm standing here and another person stands here, the same number of cars go by them every second. The frequency is the same, whether I'm in the 100 km/h area or the 60 km/h area. What's changed is the distance between the cars and the speed of the cars. In the same way as waves. The wavelength is large here, but small here because the speed is lower here and the speed is higher here. That's how frequency doesn't change. When I change the speed, the wavelength automatically changes with it. Okay, that will maintain the frequency of the wave. That's why the frequency can't change. Okay, if I change wavelength, it's by slowing something down. If I change the speed, I'm going to increase or decrease the wavelength as a result. Right, and that's what we'll be talking about a little bit more tomorrow. Okay, all right. Now, remember we saw this, okay, we talked about mass on a spring and how mass on a spring makes waves, how a pendulum can make waves, okay? So don't forget that that's the case there, okay? That's it. That's all we had to go over today. So, you're done for today. Hey, don't forget your West Ed assignments for Friday, okay? If you're not going to be here on Friday, don't screw your group over, okay? Make sure you give them your part of it, all right, so that they can hand in everything. There's nothing worse than being part of a group that gets screwed over by somebody, okay? So if you're, if you're leaving or whatever, not that you should be, but okay, make sure your group has all the stuff they need.